Welcome back, everyone, to this section of the course on feature engineering and data preparation. In the real world, not every data set is going to be ready right out of the gate for your machine learning algorithm. We often need to perform things like data cleaning or try to produce more usable features from the raw data itself. In this section, we're going to work on the large linear regression dataset we previously discussed to get it ready for the machine learning project. Let's begin by answering the question, what is feature engineering? Formally speaking, it's the process of using domain knowledge to extract features from raw data via data mining techniques. So there's a lot of keywords there. Let's kind of break that down a little further. So when we say the process of using domain knowledge, what we really mean is, as a data scientist, if you're not familiar with the domain or area of expertise that the data is from, for example, if we're dealing with that housing data set, and we're not experts in the housing market, we should probably talk to maybe someone like a real estate agent to see what features are important and what features can be further extracted from. And when we say extracting features from raw data via data mining, what we're really saying is trying to either transform features into a useful numeric feature set or trying to further break down information that can actually be within a data feature. So what does it actually entail? In general, there's three approaches we can take here. We can extract information, combine information, or transform information. Let's begin by talking about extracting information, which is probably the most common way to actually perform feature engineering. Imagine we're working with a data set with visitor expenditure information for something like a bar. So customer comes in and they spend some money on food and drinks. And what we could have is for each of these purchases of expenditures, we could have a timestamp for each row. And a full date timestamp would be in this format, where we can see 1990-12-01 and then the hour, minute, second. And in its current format, this is actually very difficult to pass directly into a machine learning algorithm. The way linear regression works, or many other machine learning algorithms work, is they're actually going to try to multiply this by a numeric coefficient. And we can't really say for this full date timestamp to multiply this by some coefficient. There's no mathematics that works there. So, as I mentioned, in its current format, it doesn't really work for us. And there's no coefficient we could directly apply. And in general, for most algorithms, what we need to do is make sure the features are either a floating point number or an integer. So this means that we'll need to actually extract the information from this date timestamp. So what that means is we could have a feature called the year. And then the year will just be something like 1990, 2000, 2002, etc. Or we could create another feature column for a month, where it'd be 1, 2, 3, 4, etc. What we could also do is start getting even more clever and discuss things like whether this particular date is a weekday or a weekend. And we could do just a new feature saying 0 or 1, is this a weekend? Or what we could do is also start integer encoding the actual days of the week, like Monday goes to 1, Tuesday goes to 2, etc. And then there's more complex examples of this as well. Maybe we have the text data for the deed of a house, or text data in general. Now we can definitely not directly multiply a string of text by a coefficient. I can't say 5.5 times this essay. So instead what we could do is try to extract numeric features from something like text data, which at first glance doesn't seem like it has any numeric features, but actually does. What you could do is take into account the length of the text, or take into account the number of times certain terms are mentioned. And this actually falls under another category called natural language processing, which we're going to discuss later on in the course. Now let's move on to discussing combining information. And we've actually already done this with polynomial regression. Recall that we could easily combine information by looking for interaction terms. And that could be something like multiplying that advertising spend feature by radio spend or TV spend. So that's one way we can easily combine information. What we could also do is combine extracted information. For example, maybe we're dealing again with that bar data set, and for whatever reason, we talk to someone who has domain experience in running bars and running restaurants, and they've come up with this feature called nightlife. And nightlife could be a feature where a customer comes in when it's both the evening time and a weekend. So maybe what we could do is have a new 0 or 1 value for this new nightlife feature, where we've both extracted information and then combined them. Now let's discuss transforming information. This is very common for string data, especially for things like categorical data that's coming into string. because most algorithms cannot accept string data directly. Again, you can't multiply a string such as red by a numeric coefficient. It doesn't make sense to say 4 times red. So often, because categorical data is presented as string data, what we need to do is transform it. So for example, what we could have is a large data set of social network users that could have the country of origin as a string feature. For every single customer, we have a country like USA, United Kingdom, Mexico, etc. So there's two main approaches for dealing with this sort of categorical transformation. There is integer encoding and one-hot encoding, also known as creating dummy variables. For integer encoding, it's quite simple. We just directly convert categories into integers. So first category is 1, second category is 2, 3, and so on for n number of potential categories. So what this would look like is, again, if we're considering that country feature where we have the string codes for the countries, what we would do is just say a map for USA is mapped to 1, Mexico is mapped to 2, Canada is mapped to 3, we see USA again, so we map it back to the original 1. And this is integer encoding. Now, a possible issue when it comes to integer encoding is that it's actually implying an ordering and relationship, because the machine learning algorithm is not fully going to understand that in this particular case, the integers are representing categories. It's always going to think of these numbers as being on some sort of linear scale. And the formal word for this is an ordinal variable, where there's actually a relationship or implied ordering between these various factors of countries. Now, we know that realistically, there probably is not, for this particular case, some sort of ordering relationship, because the implication that we're implying here with the integer encoding is that something like the country Mexico is twice the value of USA, and the country Canada is 3 times the value of USA. Now, that can be true maybe in certain situations where you're trying to do something like maybe, I don't know, Olympic prowess or something like that, but in this particular case, it's highly unlikely that we actually have that direct encoding relationship. So this may or may not make sense depending on the feature and the domain. For a quick example of something that would definitely make sense for integer encoding, could be something like spice level, where here we can see we have mild, hot, and fire as different spice levels, and there's clearly some sort of ordering within these string categories. Hot is going to be spicier than mild, and fire is going to be spicier than hot. So in this case, integer encoding definitely does make sense, especially if we are actually mapping this correctly so that the ordering is as expected, where hot is above mild and fire is above both hot and mild. You should always carefully consider the implication of integer encoding when it comes to this category transformation. We want to make sure that if we decided to do integer encoding, then an ordinal variable or something that has ordering to it was a fair assumption to make. So the overall pros for integer encoding is that it's very easy to do and understand for the most part. You're just calling something like .map and then map all the strings to a particular integer. What's really nice about it though is it doesn't actually increase the number of feature columns. We still just have that single feature column like country or spice level. It just happens to directly go from strings to integers. The major con for this though is that it implies an ordered relationship between the categories, which is often not the case. So what happens if it's not the case? Do we have another option? Fortunately, we do with one-hot encoding, otherwise known as creating dummy variables. Essentially what we do is we convert each category into individual features that are either a 0 or 1, depending if they were actually that particular category. So for example, in order to convert these categories into individual features, for the example of the countries where we have USA, Mexico, Canada, then what we're going to say is create a new feature for every single unique category possible. So notice, in this particular case, we're going to assume that there's only 3 possible countries, USA, Mexico, and Canada, which means now what we're going to do is create a feature column for each of those, and then we're going to say a 1 if it happens to be that category, or a 0 if it's not that category. And this is why it's called dummy variables, because these are not actual variables that were present in the data to begin with. USA, Mexico, and Canada, it was just country, and now we've kind of made them dummy because it's either a 0 or 1. So we've expanded the feature set, but now we don't need to worry about any implied relationship of ordinal variables. So no ordered relationship is implied between the actual categories. We're not saying here that Mexico is twice the value of USA or Canada is 3 times the value of USA. It's just 1 or 0, is it this actual country? Now, the issue of this is that we did greatly expand our feature set, and now we have many more columns. So instead of just a single coefficient, you're now going to have 3 coefficients attached to this country code. We can try to reduce this feature column expansion by creating higher level categories, and this is where domain experience really comes into play. For example, if you're dealing with a social network that has users from all over the world and in every single country, it may not be useful to do a feature for every single possible country. Instead, maybe you do higher level categories like the region they're from, like Northern Europe versus Southern Europe, or maybe continents, Europe versus Asia versus North America, etc. So obviously we can easily use pandas.map or .apply to achieve this, and later on we're actually going to see that it has the code called pd-get-dummies, which automatically creates this for us. And in general, this may require a lot of tuning and domain experience to choose reasonable higher level categories or mappings. So it's just something to keep in mind. There's going to be a little more thought and work that goes into this when you're dealing with a lot of categories. We also must be aware of something called the dummy variable trap, and mathematically, this is known as a multi-collinearity issue. Essentially, when we're converting to dummy variables, that can cause features to be duplicated. And I want to show you the consideration of the simplest possible example. So let's consider we have just a binary category. There's only two possible options. And for some reason, we have a feature here. Maybe we're dealing with packages and the way they shipped, and they have a vertical direction to them. Either they're up or they're down. If we were to one-hot encode this, notice what happens. Now we get two features, an up feature and a down feature. But the new columns are actually duplicate information with inverted encoding. Essentially, if something is not up, and in the case of binary feature set, then I know that it has to be down. So why do I bother keeping the information here from both columns? Because actually all the information can be encoded into one column, because if up is 1, then I already know down is going to be 0. I don't actually need to pass that into my feature set again. So this is easily fixed by simply dropping that last column. And in general, this issue would expand to more than just a binary categorical set. So what we can always do is, if we have two or more categories, what we're going to do is just drop off that last column. And luckily, later on we'll see that Pandas actually has a built-in parameter called drop first or drop last in order to just drop one of these columns. And we're technically not losing any information, because your information for that last column should be encoded kind of behind the scenes through every other column. That's really easy to see with the example of up versus down. It's maybe not so clear with these country codes here, but obviously if we see that USA is 0 and Mexico is 0, then it must be Canada as the other option. So there's kind of no need to encode that last Canada column feature. So the pros for one-hot encoding is that no ordering is implied, but the cons is that you do have the potential to create many more feature columns and then coefficients depending on what machine learning algorithm you're running. So you also have to take into account the dummy variable trap consideration, and it's also not easy to add new categories. So what do I actually mean by that? Let's imagine that we're dealing back with that social network data set, but for whatever reason, maybe we're starting with a much smaller social network, and we only have presence in a few countries, maybe a couple European countries and the United States. And later on, we begin to add in users who are from other countries, like let's say Japan. However, if we're thinking back to a data set like this, if someone was from Japan, a brand new country that we didn't originally encode, what we would need to do is go back and then create the new feature column for Japan, label everything in the past as 0, and then for this new user from Japan for the very first time, they would get a label of 1. So as you add in more potential future categories, you have to go back and edit all your information. Granted, this is more of a programmatic issue than it is a machine learning one. It's pretty easy to just go back and add a new column, fill it up with zeros, but it is something you always have to keep in the back of your mind if you plan on adding many more potential categories. So throughout this section of the course, we're going to be working on addressing the following issues. Things like outliers in data, missing data, and categorical data. And keep in mind, not every single issue here would fall under the umbrella of strictly feature engineering. We could also call this data cleaning or data preparation or data munging, lots of different words for this. But also keep in mind that feature engineering in general will always be data and domain dependent, especially. If you're dealing with a data set that has a lot of features on housing and real estate, the typical feature engineering tasks for that data set are going to be dependent on your own knowledge of the real estate and housing space. You can't just apply any data scientist to any data set for feature engineering. That's why it's so important when you're working as a data scientist or a machine learning practitioner to always either become an expert or at least knowledgeable in the domain space, or more likely, contact someone else and work with someone else, like a colleague, who is knowledgeable in the domain space for that data set. Keep in mind, there is no one-size-fits-all solution when it comes to feature engineering. It's always going to be dependent on the particular data set and domain dependent. All right, let's get started. I'll see you at the next lecture.